All right, I'll begin. Heavenly Father, we thank you for this day, and I just pray that you be with us today as we study calculus, that we be careful to glorify you, Lord, in what we do. You know my prayer, Lord Jesus. Amen. So I was going to start with an example that is based on the homework. So today, still just working on manipulation and calculation power series. So I want to show you guys basically some of the things we can do sort of to gain control of them and understand them. Now there's a basic principle. Here's the concept that given smooth f of x, we can approximate f of x near x naught via f of x is approximately equal to f of x naught plus f prime of x naught times x minus x naught plus 1/2 f prime prime of x naught times x minus x naught squared, and then stuff plus more terms, all right? And so the Taylor series for f centered at x naught in principle can give us a complete and accurate recreation of f near the point, right? So if I don't keep everything, if I don't keep the plus ... In fact, this, I should be more careful. This is not approximate. Like this right here, this is equal. If I have the plus ... like this, we actually have equality for appropriate x. But the subtle thing is if we do like this, f of x equals to, f of x would be like approximately if I truncate this thing. So the first approximation you learn in Calculus 1 is the tangent line approximation, right? That's the tangent line approximation to the function at x naught. And so, for example, if I want to approximate, say, sine of x, right? Sine of x is equal to what? Well, its Maclaurin series is x minus 1/6 x cubed plus 1/120. That's 5 factorial. X to the 5th plus ... Now that's straight up an inequality, right? But if I truncate that, if I say sine of x is approximately x, right? That's what we. So how can I put this? If we have a Taylor series for the function, that gives us all the terms we need to create approximations of arbitrarily high precision. The more terms we keep in the Taylor series, the better approximation we have. If we cut it off like that, then it's not going to be true. But you know what? How far off is it from being true? Like this. We have some of the tools we already need to analyze that from our previous material. Check it out. So like, what's sine of 1 in radians? It's equal to 1, right? Minus 1/6, right? Plus 1/120 minus ... right? This is what? This is an alternating series, right? So we could actually be precise about how far off we are from the real sign. For example, you guys, what if I just keep, say, sine of 1 is approximately 1 minus 1/6. Well, that's 5/6, right? So that's, the error is what? Is at most what? 1 over 120, right? That's the alternating series estimation theorem. So to to the limits of my on-the-fly arithmetic, 5/6 is what? Like 0.84-ish? Actually, that kind of matters, the ish, because this is about 0.01, right? So it kind of matters the part I can't remember. What's 1/6? Here's a backwards calculation for you. 1/6 is 1 over 1 minus 5, which is, I can't do math. It's what? 1 plus 5, maybe. Not sure that helps. Oh, I'm sorry. Let me stop doing stupid things. I had more important things.
0.16.
0.16 with a 6 repeating. So I guess this is roughly, it's more like 0.83, right? But that, I'm sure about that, plus or minus 0.1. So try it out in your calculator. What is the sine of 1 radian? Make sure you're in radian mode. What do we get? What's that? Say again?
0.8414.
8414.7? Yeah. So as you can see, look at that. The alternating series estimation theorem works. And this is probably actually how your calculator finds values of sine and cosine. Right? It can use an algorithm that's based on this alternating series. It can generate values for sine and cosine by just looking at the first few terms in the power series. And it'll be a very good approximation. Now the question is, how good an approximation? I mean, if it happens to be alternating, then we already have all the tools we need to say like how good an approximation it is at a point, right? But the better answer to that question is given by Taylor's theorem, which I'll probably cover Monday. All right. But I want to spend a couple minutes with you guys because this is like one of the major reasons we're talking about power series, is just because it gives us this tool, this way of reproducing complicated nonlinear functions with just some kind of like simple polynomial. Another good example of this is if instead of wanting to work with 1 over 1 minus x, right? Well, geometric series says that's 1 plus x squared plus dot, 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 right? So an approximation which is made all the time in physics is this. Right? So this is for x, close to 0, let's say. If x is close to 0, then the higher terms in the geometric series are very, very small. So to a good approximation, 1 over 1 minus x is essentially just that. Here, we could try it out. 1 over 1 minus 0.001 is approximately 1.001. Try it out. What do you get if you take the reciprocal? I need to get my calculator out. If I have it. I'm not sure I have no calculator, no. Oh, man. For some reason, I have this laser. Whee. So what do you guys get? So what did this actually work out to? According to your calculator? 1.001 001 001, so like that repeated. So as you can see, just keeping the first two terms in the geometric series gave us an approximation to this, which was good to like what, 5 decimal places? It's not bad, right? Now, of course, if you try to do this for like a half, well, it's not going to be as good, is it? This is what? This is 2. and this is 1.5. So you see this approximation only works when x is really close to 0. It starts failing the further you get away from there. All right, so enough of that. I'll give you more precise descriptions of how we can judge the error in a Taylor series come Monday. And I'll actually prove what's called Taylor's theorem then. But for now, I want to talk about, let's look at something like this. F of x equals to, let's say, 1 over 6 plus x. I want to center power series at a couple different points, just to kind of show you guys what goes on here. So part A we'll do at 0. We'll center it at 0. Part B, we'll center it at 1. And part C, we'll center it at -3. I think by then you'll be sick of this problem. Okay? So basically every time we're going to use the geometric series result, which is that a over 1 minus r is the sum n equals 0 to infinity of ar to the n. Right? Let's see here. So how about, to start with, can you guys tell me what I need to do? What's the trouble with this expression as it starts? Well, there's the minus, but what about the 6? Right. Pretty much I agree with you. I'm going to say factor out a 6 from the denominator, right? Now I'm going to take Nathaniel's advice and make it a minus. And there you got to use your imagination a little bit, but that's 1 over 1 minus x over 6, right? Why am I doing this? Just so I can apply the geometric series result, right? I have to match up with 1 over 1 minus r, or a over 1 minus r, in order to use the geometric series result. So this is then what? This is 1/6, the sum, n equals 0 to infinity of minus x over 6 to the n power, which I will reformat as, tell you what, I'll bring the 6th inside. That's the sum, n equals 0 to infinity, minus 1 to the n, right, divided by 6 to the n plus 1, and that's all times x to the n. And there you go. That is the power series centered at 0 for this function. Does that make sense? Now, what's it good for? Let me ask a better question. What's the interval of convergence of this series? Going back to our first and most uninteresting day on this topic so far. To go from here to here, what condition do I need? I need that the radius is less than 1. What does that mean here, though? That's my r, right? So I need minus x over 6 less than 1. But by properties of inequality, by properties of absolute value, that just gives me this is less than 6, right? So this is going to be good for basically minus 6 less than x less than 6. In other words, the interval of convergence is minus 6 to 6, neither of those being included. Okay? Yeah.
Oh, wait, you're going to show, I was about to ask how to center that.
Oh, yeah, we're going to do that. So that was part A. Okay. Part B, let's see here. We start out basically the same place. So the way I like to do it is just, if I'm going to center at 1, I subtract 1 and add 1. But let me just be more to the point. That's 7 plus x minus 1, right? So to expand, to center the series at x not equals to 1 means to, in other words, to expand in powers of x minus 1, right? So I need to create that x minus 1 there, and now we're kind of back to the same trouble we had in part A, which is that I need a 1, but I got a 7. So pull a 7th out, right? Like so, right? Now we've got it in the right form. It's basically in the a over 1 minus r type form. You can see what the radius is, or the ratio. So this is going to be equal to 1/7, the summation, n equals 0 to infinity of minus parentheses x minus 1 over 7 to the n. And that's going to be for whenever the absolute value of x minus 1 minus over 7 less than 1, right? But of course, this condition we can clean up a bit, right? It's really just the absolute value of. Do you guys know how to think about that? Like, how do you think about when I show you the inequality, absolute value of x minus 1 is less than 7? Does that mean anything to you geometrically, you guys? Do you understand how to think about that geometrically? Here's how you should think about it. The distance from 2 points in the real number line is the absolute value of b minus a. This is distance from a to b. So when I see this says the distance from x to 1 is less than 7. I mean, of course, you can also unwrap that. That's minus 7 less than x minus 1 less than 7, which if you add 1 across the inequality gives us minus 6 less than x less than 8. So in other words, the interval of convergence here is minus 6 to 8, not included. Wait a minute, you mean the same function can have different intervals of convergence? Yes, I do mean that. The center of the series changes the story, right? Now for a given center, you're going to find a particular interval of convergence. It's not going to change depending on how you do the calculation if you do it correctly. But if we change the center of the series, then the interval of convergence must also usually modify. Okay, so we're not one more step here. This is the sum. N equals 0 to infinity. Minus 1 to the n over 7 to the n plus 1, x minus 1 to the n. There you go. That's the power series for the function centered at 1. All right, one more to go. So if we want to center, we want to expand in x plus 1. Did I say minus 3? Oh, x plus 3 then, right? AKA at x naught equals to minus 3, right? Because we always expand in x minus x naught. So if you're expanding at minus 3, that means you're looking for x plus 3 powers in your power series. So this is 1 over 3 plus parentheses x plus 3, right? Well, this is like all 3's all the time. Look at this. So we factor out a third. And then we get 1 plus x over 3. It's very, lots of 3's. Let's see here. And then same as before. If you don't mind, I'm going to skip a step here. And we can pull the third inside, right? And this is going to be for what? Oops. What's the condition? We need the absolute value of minus x plus 3 over 3 to be less than 1, aka absolute value of x plus 3 less than 3, which is to say that x is an element of, you know, well, 0 to 6, right? Well, wait a minute, no. Fine, I'll write it out. Minus 3 less than x plus 3 less than 3, which is to say minus 6 is less than x is less than 0. Yeah, so the interval of convergence here is minus 6 to 0. We can anticipate all of these things graphically, all right? So like if you look at what this function is, what is this function? We're looking at y, I mean the total function here, y equals to 1 over 6 plus x. Where's the vertical asymptote for this thing? Right. So what's going on here, and let's see, what's it look like x if it's positive over here. So the graph actually looks something like this. So what's going on here in part A, right? In part A, we were centering the series at 0. And we found that this was the interval of convergence from part A, right? It was, I've lost it, minus 6 to 6, right? That was from part A. It makes sense. It's symmetric about the center. And it goes as far as it can before it gets into trouble with the vertical asymptote. And then when we centered it at 1, what happened? We got minus, what? Oh, what? Sorry, I'm having trouble with my own thinking. When we centered it at 1, we still got stuck at minus 6, but then since our center is over here, we got to go out a little further, right? And then in part C, since we centered it at minus 3, that was the smallest interval of convergence altogether, right? We just went like this there. That one was this one. So what's the radius of convergence in each one of these cases? R equals to what for part A? 6, right? What's the radius of convergence here? It's 8, right? Is that right? Oh no, 7. 7. 7. 3. Any questions? I just wanted to go through an example like this carefully and slowly because it's an important example, right? Let's do another sneaky one like we did it last time. Let's find the power series for, let's say, what if we tried f of x equal to, oh, here's one. This one's just based on what we've already done. What if you have g of x equals to, say, x squared times 1 over 6 plus x? So this is very much related to the ones I've just done, right? Suppose I want the power series centered at 0. It's pretty simple, right? I just do what I do what I did before, and this is what? I already know what that is. It's right there, right? It's sum n equals 0 to infinity minus 1 to the n. I remember that part. X to the n. I think I remember that part. And then I want to say 6 to the n plus 1. Did I get it? Am I right? Okay. Phew. It's a relief. So then how do you do this? Well, good news. You can multiply a series in the most natural way. You just bring it inside, multiply that, and so this is nothing more than sum n equals 0 to infinity minus 1 to the n over 6 to the n plus 1 x to the n plus 2. And there you go. That's the Maclaurin series centered at 0 for this function. Of course, you could have pretty much done the same calculation I did in part A, and you could have thought of, if you put x squared here, you could have thought of x squared as being the A and just done it by direct geometric series, just the same, right? Here, let me do something a little bit weirder. Example 3. What if we had h of x equals to x squared over 1 over, oh, you know what? Let me stop with the weird examples. It's too weird. Example 3. So I'm going to go back to something we did last time. So consider f of x equal to the inverse tangent of x. Now, I guess my question to you would be, do you want to calculate the Taylor or the Maclaurin series of that directly? Finally. Think about what it would mean to calculate the Maclaurin series of this directly. Do you want to calculate the first, second, third, fourth, fifth, sixth, nth derivatives of this function to evaluate at 0 to figure out the power series? I don't. But what I do want to do is notice that if I do df dx, I get what? 1 over 1 plus x squared, right? Well, that's not bad because that's geometric. This is the sum minus x squared to the n equals 0 to infinity, right? Recognizing r equals to minus x squared, right? Use geometric. But then what? That gives me that df dx is equal to the sum n equals 0 to infinity minus 1 to the n x to the 2n. And then how do I find the power series for inverse tangent? Exactly, I just integrate. It sounds like I'm saying disintegrate, but so this would give us that inverse tangent of x, which is my f, right, is equal to some constant, we don't know it yet, it's 0, plus, but we should figure that out, sum n equals 0 to infinity minus 1 to the n. Integrate term by term here, what do we get? 2n plus 1, so I have to divide by 2n plus 1, x to the 2n plus 1. Right, if we set x equals to 0, then we get inverse tangent of 0 is equal to c plus the sum of 0. So this is 0. So therefore, c is equal to 0. Again, the thought process here is that that power series has linear and higher terms. So when I plug in 0 into it, I get the 0 series. You should understand that the reason I'm going through this step is that there are functions where that constant term matters, and if you neglect it in this calculation, you'll be wrong. We just got lucky in the sense that both of the constants that we've worked out with this trick so far have been 0. If you've got a function whose value at 0 is not 0, then it's a different game. Anyway, so we got it. The power series for inverse tangent is thus the sum n equals 0 to infinity of minus 1 to the n over 2n plus 1 x to the 2n plus 1. In other words, the first three terms, let's see here, put n equals to 0, what you get? We get x, right? What happens when we put n equals to 1? That makes this a minus, that makes this a third. So we get minus 1/3 x cubed. What's the next term? Plug in n equals 2. 2 times 2 plus 1 is 5. So I get 1/5 x to the 5th. So this answer is kind of odd, right? I'm sorry, that's awful. I apologize. But there you go. That's the power series for inverse tangent. So let's see, like what have we found power series for at this point? Sine, cosine, exponential, hyperbolic sine, hyperbolic cosine. The inverse tangent, last time we get log of 1 plus x through a similar trick. Then of course we can combine these and do interesting things. An example I haven't done yet, there's two kind of central examples I haven't done yet, which are kind of shocking when you see them. But think about this. What if you were asked to integrate, say, x to the 10th times the inverse tangent of x? Now, if you go back to our, our list of calculations at the start of this course, I would be scared if somebody asked me this. I mean, like I would integrate by parts. And I might even be able to do it. If I integrate it with parts, it might actually work out. But it'd be awful, right? So yeah? Oh, no, just stretching. It's cool. So check it out, though. This is actually the integral of the summation, right? N equals 0 to infinity. What's the power series for x to the 10th times inverse tangent of x? All I got to do is just take what I have here, right? And do what? Increase the power of x by, like that, right? Just multiply this series by x to the 10th. That's the power series for x to the 10th times inverse tangent, right? Using example 3. So yeah. Of course, if you'll allow me, I'm going to clean it up at this step. So this is actually x to the what? 2n plus what? Plus what? Plus 11. Thank you. Then we use the term-by-term integration theory. What's it get us? Theorem. We get some constant plus the sum, n equals 0 to infinity, minus 1 to the n, divided by 2n plus 1, divided by 2n plus 2, x to the 2n plus 2. There you go. That's the integral.
Wait, 2n plus 12 or 2n plus 2?
Oh, plus 12. And same down here. I can't read my own writing. Thank you, Nathaniel. So, like, there are other examples. I told you guys earlier that we couldn't integrate e to the minus x squared, right? It's no longer the case. See, because this is now the integral of the sum, n equals 0 to infinity, minus 1 to the n, x to the 2n over n factorial. So what I'm doing is I'm plugging in minus x squared into the exponential series. I'll write it over here. So like e to the u is the sum, n equals 0 to infinity, of u to the n over n factorial. So if I set u equals to minus x squared, u to the n is minus 1 to the n, x to the 2n. And that's why I wrote this here. So then, what happens? Integrate term by term, and there's your integral. So with power series, all these functions which are integrable and yet don't have nice antiderivatives, well, here's the not so nice antiderivatives. You can find them with series. It's not a big deal. Now, the disadvantageous part about this is that, well, I don't know, they're series, so it's kind of a little bit uncomfortable. But on the other hand, it's not that bad a thing because this actually gives you a prescription for how to approximate the integral of e to the minus x squared to as good a, if you want to find an approximation to the function, which is the antiderivative of e to the minus x squared, this gives you this gives you how to do it. And you can do this stuff order by order just the same. Like I could also look at this in terms of just the first few terms. I could say, well, that's really just like integrating 1 minus x squared, plus stuff. And so a good approximation to the integral would be x minus 1/3 x cubed plus stuff, So I guess I should put the constant first. So there you go. There's an approximation to the antiderivative, just integrating term by term. This is something we couldn't do before, right? think that's weird? What I'm about to show you. All right. This problem I'm about to show you, students tend to find challenging. So stick with me here. So let's see. Let's consider. Let's think about f of x equal to x to the 10th times the inverse tangent of x. All right. So I had the power series for that right over here. Right. We wrote it down a second ago. This has, power series representation centered at 0. Sum n equals 0 to infinity. What is it? Minus 1 to the n over 2n plus 1 x to the 2n plus 11. Right? So here's the question. Find the 99th derivative of the function at 0, and also find the 100th derivative of the function at 0. How would you do this? So it goes back to what we did last time, right? Last time we showed that if the function's analytic, if it has a power series like this one does, then you can also express it in terms of the derivatives, right? Let's say k equals 0 to infinity of the kth derivative of f at 0 divided by k factorial times x to the power k. So my question, so you gotta play a matching game here, right? The powers that are available. The question is, can we have x to the 2n plus 11? Can that match x to the k with k equals to 99 or 100? In other words, you just try to solve. Is 2n plus 11 equal to 99 for some choice of n? What n does that give you? Right, 2n equals to, what'd you say? I'm sorry.
I'm sorry, 48.
What's 99? What's 99 minus 11? 88. Okay, so you guys told me that n was 44. Okay, I'll buy that. On the other hand, that's case number 1. Case number 2, if you look at 2n plus 11 equal to 100, well, that says that 2n is equal to 89, which means no solution. See, because if you get n is 45.2, there's no 45.2 power in the power series expansion, right? You're looking for whole numbers. If it's not got a whole number solution, that just goes to the fact that there is not an x to the 100 type term in the power series expansion of x to the 10th times inverse tangent x. That's not surprising, actually, because this is an odd function. So it only has odd powers in its power series expansion. But this is something. And so we can get from that, and we put in n equals to 44. We've got 1 over 2 times 44 plus 1, right, is equal to the 99th derivative at 0 divided by what? What's k? 99. And so that gives me that the 99th derivative at 0 is simply 99 factorial divided by, well, 89? Yeah. On the other hand, what's the 100th derivative at 0? Right. Well, the fact that there's no solution to this equation means that you can't find there's no non-trivial term which exists, right? There's also other things, like there's all of the terms that don't appear here have 0 coefficients, is the way we think about it. So it follows that this is just equal to 0, which is to say that there is no x to the 100th in the power series. So there's no 100th derivative. Here, I'll show you a lower tech application of this example if I have time. I may not. I think we got time. I mean, so if you don't know about the trick I just showed you, this is a very scary question to be asked, right, on a test or something. But it's actually really just a way of seeing if you really understand how to manipulate Taylor's theorem and understand it, and, well, some stuff like that. Listen, if I have f of x is equal to 3 plus 2 times x minus 1 plus 1/7 times x minus 1 squared plus 1/4 times x minus 1 to the 6th plus dot, 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 dot. If I have this power series expansion for f, from this I can read derivatives. From this I can tell you f of 1 is 3. I can tell you f prime of 1 is 2. I can tell you that f prime prime of 1 is 1/7. Why am I wrong? What are we supposed to be comparing to? We should be comparing to the generic thing, which is f of 1 plus f prime of 1 times x minus 1 plus 1/2 f prime prime of 1 times x minus 1 squared plus da da da. Eventually we get to 1/6 factorial, the 6th derivative at 1 times x minus 1 to the 6th, and so forth. So that's not right. We have to solve 1/7 equals to 1/2 times f prime prime of 1. So it's not just 1/7, it's what? Yeah. And what's the 6th derivative at 1? We got to solve 1/4 equals to 1/6 factorial times the 6th derivative at 1. So in other words, it's going to be 4 over, oh wait a minute, I'm an idiot. It's going to be 6 factorial divided by 4. What else? What other? There. You know, this is low-hanging fruit here. You can pick it. You guys tell me what these are. Fill in the blanks for me. It is our custom that those have to be 0, right? Because there is no third, fourth, or fifth derivative terms in the expansion. The custom is, when you guys write this out with plus dot dot dot, these are the terms of the agreement. This notation means that this is all the terms up to order 6. All right? You are not allowed to start writing a non-trivial fifth order term over here. That is against the rules. So when I have this is proof positive that the 5th, the 4th, the 3rd are not there. So they're 0. So I will continue on Monday. I'm not following the book. I'm trying to show you guys how we calculate with these things, example after example. I'm not sticking with one thing. I'm bouncing around a bit. Yeah. I hope that helps. If not, I'm sorry. I can go back to theory building if you'd like, but I don't think it's a good idea here. Yeah, you can hit it. Have a good weekend.